when we think about knowledge representation, what do we mean by knowledge representation? So, knowledge representation means there is stored information within the model and which can be used to interpret, predict and appropriately present to the outside world. So, I repeat again, knowledge representation means there is stored information or models used by a person or machine to interpret, predict and appropriately present to the outside world. So, let us write this down. Let us write this down. This is stored information or models used by a person or a machine to interpret, predict and appropriately present to the outside world. So, when we think about knowledge representation, there are two facts which come within our mind. One, we need prior information or some known state that the machine can learn and it can store this information. Then we need observations to probe and learn new information. Right. One is prior information which you require to learn, and then the machine has this information embodied within the engine, and then we need observations to probe and learn new information. So, what are we learning? I mean, this is another question that comes into our mind. What is learned? We say there is an environment and it is giving you some features, some signals, and from which you can extract information and you can store that information within the network. And what are you learning in the process? We are learning the biases and weights of the network. In other words, we are learning the parameters of the network. And you may ask this question, how is it learnt? Right, I would just say, how is this learnt? So, this is learnt through a measure or a metric that guides the system to align best to the data. Right. So, when we think about any learning process, there is an objective metric that drives the system to learn the information and makes the system best aligned to the data. Right. This is very qualifying statement. So, we can get into the details of quantification as we introduce the measures for knowledge representation. So, let us start with some simple rules. Okay. Rules for knowledge representation. So, we will start with rule 1. Similar inputs, that is patterns that are drawn from similar classes should have similar representations inside the network. And well, you can also extrapolate saying they must belong to the same class. A good example is, suppose we want a learning machine to learn colors and group the colors together, and we want maybe to learn animals and group the animals together, then we have to have them clustered accordingly, which means that they should have similar representations inside the network. So, there are plenty of measures one can think of. So, let us discuss a couple of metrics. So, let us discuss a couple of metrics. So, to start with, I have a vector x suffix I which has m attributes, right. There are m coordinates x I1, x I2 dot 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 x I_m. This is one vector, and I have another vector xj, which is xj1, xj2 dot 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 xjm. So, we assume that they have the same coordinates. Now, we formulate a distance metric between these two vectors xi and xj given by the L2 norm distance between xi and xj, right. This is given by this equation. You take the difference between the coordinates xik and xjk, square these up, sum these over all the attributes k equals 1 to m, and then you have a square root here, right. One can think about different norms, and L2 norm is a common metric. And if you look into the mathematical methods and techniques for signal processing course, there is a detailed discussion about various norms and the geometry behind these norms. We have another measure from this, and the measure is the inner product. So, our second measure is the inner product metric. So, the inner product between two vectors xi and xj is basically given by the familiar dot product, which we are aware of. It is xi transpose xj, which is pairwise product over the coordinates k for these vectors I and j, right, and then you sum this up, k equals 1 to m. There is a link between the inner product metric and the distance metric, and we will get into that in a little while. But you can kind of imagine that smaller the Euclidean distance, larger the inner product. So, let us quickly see this. Let us suppose that the norms of these vectors are 1, right. Both xi and xj have norm 1. We consider the square of the distance between xi and xj, right, and this can be given in terms of the inner product, which is now the induced norm of the difference vector squared, which is xi minus xj transpose times xi minus xj, right. Basically, you take a deviation of these two vectors xi minus xj, and then that forms your error vector, and you basically take the induced self norm. Now, this can be written as, let us expand this xi minus xj transpose times xi minus xj. So, we get norm xi square plus norm. So, you have xi with xi and you have xj with xj, and then you have these cross terms. So, if you simplify this, we have norm of xi square plus norm xj square minus 2 times xi transpose xj. I mean, if you are savvy, you will see that in one case you have xi transpose xj, in other case you have xj transpose xi, and since it is a scalar, it is the same. So, therefore, you can have it as xi transpose xj. Now, we will use this property here, that the individual norms are 1. So, this is going to be 2 times, this is going to be 1 plus 1 minus 2 times xi transpose xj, which is 2 minus 2 times the inner product of the vectors xi and xj. So, if you just simplify this, this is 2 times 1 minus the inner product of xi and xj. So, clearly as d goes up, the inner product comes down, and vice versa, as d is going down, the inner product goes up. And one can think about this in terms of geometry. Suppose I have this vector xi here, and I have another vector xj here, right, and I can complete this triangle like the way we have done in high school geometry, and we take this projection of xi on xj, and that is this length. And then we also have the difference vector and given by xi minus xj. Right, and so we have a minus, we can have a minus xj in the other direction. You complete the parallelogram, and then you can come up with the vector which is xi minus xj. Right. So, if the distance goes up, the inner product comes down, and if the distance goes down, the inner product goes up, and this is the relationship between the distance and the angle measure. Now, for stochastic inputs, the square of the distance between two vectors xi and xj is linked via the covariance matrix, and this is given by xi minus mu I transpose C inverse, which is a covariance matrix inverse, times xj minus mu j, right, where in fact we can say mu I and mu j to be the same. So, I can skip this, we can have this way, does not matter. So, mu I is expectation over xi, right. Let us assume that xi belongs to a certain class with a certain distribution, and mu I is its statistical mean, which is also a vector. Mu j is the expectation over xj. If xj has a certain distribution, it is it is a statistical mean. You take the statistical mean over xj, and then the covariance matrix C is the expectation of xi minus mu I times x I minus mu I transpose, right. So, if the points xi and xj come from the same class, then their means mu I and mu j are the same. If xi and xj belong to the same class, mu I would be the same as mu j, because when you take the statistical mean, it is over the same distribution. The distribution of xi and xj are the same, and xi and xj are just points within this distribution. So, this is the same as mu. So, you can write this distance as just xi minus mu transpose covariance inverse xj minus mu. And you may question, when you bring in this covariance matrix, I considered just the xi, right. I look at for all values of I and j are subsumed within this definition of this matrix, right. So, there is no reason to have otherwise we will have to look at the joint expectation of the random variables xi and xj if they belong to two different classes, right. We start with rule 3. Rule 3 states that items to be categorized as separate classes should be given widely different representations within the network. I would say this is rule 2, not rule 3, because the prior rule was rule 1. So, this is going to be rule 2. Okay. So, this means that if you have items to be categorized as separate classes, they should be given widely different representations, because you do not want to have fuzziness between the two classes. We have the next rule, which is rule 3. If a particular feature is important, there should be large number of neurons to represent it. So, this is a sort of a heuristic rule. I mean, if you feel that a certain feature is important, then there should be larger number of neurons that should be associated to represent this feature because it is important. Then we have rule 4. Prior information and invariances should be built into the design of the neural network. So, I will discuss what these invariances are, etc. And this is very important because you have to embed prior information and invariances into the design of the network, and this can help simplify design towards better accuracy, right. This can help simplify the design of the learning machine and improve the accuracy. So, these are all qualifying statements, and I think this is this has to be kind of folded within a mathematical framework as to what we mean by prior information, what we mean by invariances, etc., and how we can fold that within the design of the network. There is a biological reason for rule 4, and I will state that. Rule 4 is important for the following reasons. One, biological systems such as the visual / auditory network are known to be highly specialized. And the way we think about the visual network, for example, we have an image of a cat, and this cat's image is rotated 30 degrees or 90 degrees, or the cat's face is elongated, right, and we can still figure out that it is a cat, and we have this invariance built in within our learning network, right, and this is very important. And second, if we have a neural network which corresponds to a highly specialized structure, then we need smaller number of parameters for learning this. We need smaller number of free parameters to learn this structure as opposed to a general network which could be fully connected. So, what it means is if we have smaller data set for training, this implies it is faster learning. Okay. So, I think you should not confuse this with one of the rules that I presented earlier, which said that if a feature is important, it should have larger number of neurons. So, a feature could be important for both a general network as well as a specialized network, but if it is specialized, then we need a smaller number of neurons, or rather the network is not so complicated, it is not very fully connected. But if it is a general network that you want to learn everything, then it has to be fully connected. This is one important empirical statement that you will have to kind of bear in mind when you design the network. Okay. Now, there is another rule which is rule 5. One has to build connections within the network so as to accelerate the rate of information transmission, right. So, we are learning data and we are learning information, and this is passing through this network, and if we have all the connections and we think certain connections are not required because this information need not be passed, then we can cut those connections so that we can accelerate the rate of information transmission, because this information is flowing through directed graphs, right, and this is very important than to have a very general structure to have all the connections, and we can figure out and prune the kind of connections. And when we think about deep neural networks and the ways in which we kind of build in the connections, we talk about how this can be incorporated.